Okay, so the idea is we've been working on FPGAs, like I was saying, which are a bit far from main concern of the ASIC community. Right? It's really hardware-oriented stuff, but we are doing it in Smalltalk, and we've been doing it for years, and we've been ahead of schedule. And the problem is, we had a real benefit from using Smalltalk to do that. And now, because of our legacy code, we are suffering a bit because it's evolving very quickly, and it becomes hard to adapt our software. So it's a kind of experimental work, and could be related to some component-based approach, as mentioned on the first session. This is an overview of the domain. So we have some hardware stuff here. You can see some small logic functions, let's say adders, multipliers, that kind of thing, very low-level things. Yes?
So what is FPGA?
FPGA stands for Field Programmable Gate Arrays. So it's an array of small gates, electronic gates, and it's field programmable because you can change the behavior of your electronic device after delivering it to the client. That's it. Yeah, arrays, I should have mentioned it. And the lines here are basically some wires, electronic wires. So the idea is this is a kind of hardware template, and you want to implement some functions on top of it, high-level functions. So the idea is you will program the basic compute nodes, and you'll have some connection paths to be set up. And after that, you'll generate something like I want to make a subtraction here, an addition here, and then I can generate a kind of 3 inputs functions. And basically, it's a small hardware blocks are very, very simple. And this field is very efficient. The main idea is you can have 100 speed up compared to classical execution or commercial PC. Right? That's possible. This kind of hardware is evolving very fast, so you can have embedded processors, sensors, a lot of new stuff appearing here. And our business is to provide a way of programming it quickly from high-level code. Okay? And we have to support all this evolution because vendors are providing new hardware every time, and we have to do that. So this is flexible hardware because you can change its functionality. It's a good thing for time-to-market delivery for products. You can start designing your circuit before having the full specification of your, let's say, video decoder stand-up. And you will just adapt some few things after that. But it's hard to program and it's hard to debug. So for those of you who attended last year, I presented something related to that for how to debug that kind of thing. This is a snapshot of commercial tools. So you can see it's a lot of resources, some functions, some memory blocks, RAM blocks, that kind of things. And of course, you have to provide some automation here because it's not handleable for a human being. So you have to provide some C to circuit translator. It's referred as high-level synthesis. You'll have to provide some debug facilities and, of course, benchmarking because clients want to choose best implementation. This is core legacy code. It's workable. You can see the matrix. You have used resource in blue, and if I zoom in, then you see what we have. So we have some function registers, small memory units, and a lot kind of switch matrix. Okay. So we've been working, as I said, in that field for years, and we have to load more, and devices are becoming more and more complex every year. And of course, Murphy has kind of have a framework working for one generation, and then something happens, someone discovers a new device, and then nothing works anymore. So the idea here is refactoring is not enough to kick into race. We have to redesign the full set because it's too hot basically. And then we have to shift from something that we had, which was a generic template that we could customize on demand, from something more component-based, with models, algorithms, components, and of course the key issues are here: performances, scalability, flexibility, durability, kind of things. So this is my order of presentation. So the legacy is here. You start with SQL, right? So I compile some kind of SQL and I get a kind of AST. I have to move some nodes, balance, depending on the available resources, so it's something classical in terms of compilation. I have to inject some idle nodes to balance the delays in the graph. And after that, I'll move to the real platform. And my nodes are here, right, in red, and my switch matrix. And after that, I move of course to circuit, real circuit. So you have two steps here: high-level synthesis, starting from C and generating what we call netlist, and resource allocation, which is starting from some netlist and producing the resources. The second point is basically something like, I want to partition my netlist. I want to flow point, try to optimize space allocation, to have an in-depth placement mechanism and routing resources allocation, as I've shown in one of the previous slides. I have the application here. Let's say either color. I have my template for architecture here, and what I want to get is something usable to program the hardware. So it's something very well known. You can have similar approaches for processor. Let's say Lisa is something like that. You have the specification of the processor, and then you generate a compiler for the hardware. We have something similar here, but a bit more complicated because the compilation play is more complex due to the other resources we have. So what we have is something like I describe my hardware. I compile it and I get my model instantiated. After that, I will have some algorithm working on as a matter of model transformation, basically. Well, this is not that important, but we have, let's say, something like the operating system support here for allocation, on-fly allocation of resources. And I have my description of my binary description. And after that, well, I can program my hardware, this one with my application, which is a SQL. And of course, here we have simulation capabilities, debug capabilities, that kind of thing. Here are some examples. So you can see these were exactly extracted from the same template, but we have different architecture here. Different vendors, different architectures, different FPGAs, and the routing algorithm is working here to find some paths between some classic other resources. Now we have to redesign this. Why? Because because depending on what you want to do, you want to focus on some properties of your model. You do not want to carry all the knowledge you have regarding the architecture for, let's say, delay estimation or maybe power consumptions. So you have, it's something like generating SQL views, right? You have to focus on one aspect of the model. And then you have to describe some algorithms here and ways of extracting information for some aspect-oriented sense. Once we have something like that, we have the model-to-model template, and we have to generate something based on transformations, a sequence of transformations to start from one model to another model, which is more suitable to some algorithms. The important thing here is we use exactly the same model to describe the architecture, the application, any of the intermediate models for aspect-oriented sense. So that this is described as, well, you can see here you have composite importance, like I was saying, you have connections, you have elements, you have connections, like I was saying, and this is highly valuable because once it's a kind of restriction of the component-based thing we had on the first session. As we are using exactly this model, then we ensure that we can guarantee contracts are valid. So as an example, I'm taking some portion of the previous model and I'm able to generate all my netlist here. So my netlist can be some kind of modules, hardware modules, or simple logic gates. We can have some composition here, and connections is a link between output pins and input pins, or several input pins. Keeping exactly the same thing, I can generate a model for my target. So I've moved from a model for my application to a model for my target. It's exactly the same formality, so I can manipulate it exactly the same way. So keeping in mind the previous schemats for FPGAs, you'll have some composition here, and you'll have some patterns for composition, let's say arrays for basic composites or that kind of things. You have inputs, output pins we'll use for resource allocation based on the netlist. Of course, once this has been done, we had to ensure portability for all legacy code. So we had to inject many of our classes, existing classes, into the framework. So the old model was something like that. We had the hierarchy here, and we have to attach some of the classes to the new hierarchy. And I'm now getting to the conclusion. If I try to summarize this, I know this is not easy to get for non-hardware people, but what's amazing is we have exactly the same tool, and it has been working for different architectures. I mean, it's not only different architectures, it's also different technologies. This is CMOS FPGAs. These are carbon-based nanotubes, nano devices. It's exactly the same, right? And these load wires here are exactly the same as these ones. While within the box here we have a nano function. So it's different. It's nano wires, junction, but it's still working. And of course, we had to implement some new algorithms for that. Right? So resource allocation cannot be the same. So we succeeded in doing that and keeping new algorithms and making them work in a global flow, while combining algorithms is something fully new for this community. Right? Domain-based exploration is well known, but the ability to shift algorithms is something new. And FutureWorks is pushing forward this kind of things for tool integration. Let's say if you want to change the graphic visualization, we use MDE. If we want to make some domain-specific optimization, we have redeveloped some new algorithms. And of course, this also needs some test coverage. And at the end, the main goal is to be able to pick and place some algorithms and to drop algorithm on top of the architecture to make the full flow appear. Thank you. Any question?
We have one. Like you said, performance improvement. I suspect that there was something very difficult that maybe you're not properly addressed. So why do you feel that you can improve the performances?
For several reasons. The first one, which is some algorithms are very outdated now, and we have some new, more performant algorithms and papers, and we want to replace some algorithms. That's the first issue. And the second one is for specific technologies, you have to customize your algorithms. And I know it's still something like a store search or that kind of thing in the domain to find connections. It's great to generate, but not that efficient.
So at some point you said the technologies have advanced so much that you couldn't just refactor to improve your environment, you had to redesign.
Yeah.
Now, because the exponents of agile methods would say, well, you can always redesign by a sequence of refactories. You just take that redesign in small steps, and you always have a working system.
Yeah.
But you didn't feel that was possible in this case, or desirable?
I've tried managing that way. It has been done partially, but now I think you cannot get something very well suited to a new technology as fast as required for commercial contracts. So we have to get something more pluggable, and this goes through a new redesign. So I think we could move on by refactoring and will fix some issues, but not the core of what we're doing. But I agree, that's something I teach to my students. Get something working and do it.
Yeah.
Okay, thank you.